Um, okay, I'm going to turn it this way and put it a little bit up just so I can, oh, no. Okay, so I can stand up while I'm presenting. Before I get into the presentation, I wanted to just talk a little bit about why I decided to do this presentation. So I've seen the einsum function around, just like doing normal work. And recently I was implementing for some personal like project that I'm working on, like a common filter, but one that I wanted to do like batch learning on. So you would have like multiple different time series that you would fit common parameters for. And it's a lot easier to implement something like that with an einsum function than it is to use the normal standard functions that are out there. So I decided to work on it, and I really like it for that application where you're doing like simple tensor operations. And so I don't think it's like the einsum function is like an amazing thing that's going to change the way you guys develop or do your work, but I do think it's something worth knowing about, and maybe it will save you some time, and it will definitely make your code simpler if you have to use it for something. So what are we going to be talking about today? So there's 5 parts to the presentation. What is a tensor? Why is the einsum function useful? An introduction to Einstein summation notation, an introduction to the einsum function, and then examples of using the einsum function. Today, you guys, I'm going to ask you guys to do a little bit of math, so you're going to earn your lunch. Yeah. So what is a tensor? So before talking about tensors, I wanted to talk about matrices and start with like, what is a matrix? There's a lot of different interpretations actually of what a matrix is. And one of them, which I think a lot of us who do machine learning think about it as, one sec, guys. Nice. I'm gonna just move this so the HDMI connection is very finicky. If I do this. Sorry, one sec. Yeah, and we're experiencing. I didn't realize it was going to be this finicky.
Bring another HDMI cable down.
I don't know what is causing it. It's like it's I think if I do it, that will help.
It's pretty weird.
I don't know. I also don't know why it was working before. What if I do this?
Yeah.
Does that work?
Oh, there we go. I'll hold it right there.
Okay, I still want to be able to see what I need to be able to present this board. So I'll just. What did I even do that made this? Technical difficulty. Okay, let's try putting it on the chair. Yeah. Okay. So let's start from the beginning. First, I wanted to talk a little bit about what is a tensor. One way that we think about a tensor as people who do machine learning and data science is as a representation of our data. Like, here's a very pixelated picture of Abraham Lincoln. And actually, when you translate it into what a computer sees, it's just a matrix of numbers. But also, a matrix can be viewed as a linear map. So it's mapping from one vector space to another vector space. And the matrix itself is what describes the vector space that you're mapping to. And the main reason why I brought this up is because there's this term for tensors called rank, and then there's a term for matrices called rank. And the term for matrices is very different than the term for tensors. In fact, it's much more complex. So, and I just want to explain it and have it on the side. So what is matrix rank? Rank is the number of linear independent vectors that span the vector space described by the columns of the matrix. So as I said, like if you look at a matrix as a linear mapping from one space to another, then the matrix itself defines like the output vector space. And here you have two columns. One is 1, 0, and one is 0, 0, but you actually only have one linearly independent vector, which means the rank of the matrix is 1, not 2. And the reason why is because 0 times this vector is equal to the other one.
So had that not been 0, would that change the rank?
If this was 1, if this was anything besides, basically there would have to be a number here,
right,
for this to have a rank of 2. But
that the scalar product between the two pulses. It's not well defined because it's 0 vector. But normally when there's some finite overlap, it's scaling. Scalar product is non-zero, then up and 0. Independent rectangular.
Yeah. It's basically that, because when I was thinking about, I was like, shouldn't the 0, 0 could be part of any basis, but actually it doesn't count because you can multiply any vector by 0 and get it. So it's not considered a possible basis vector. But anyway, so that's matrix rank. Has to do with the fact that this is a linear mapping. So what is a tensor? Wikipedia says, in mathematics, a tensor is an algebraic object that describes a multilinear relationship between a set of algebraic objects related to vector space. So like a matrix, a tensor, according to Wikipedia, is like a set of linear mappings, or a linear mapping, but like that has many axes. But that's actually not. Oh, well, first. But I actually brought this up to show like this is actually quite a complicated definition, and it also doesn't really encompass how we view tensors when we use them when we're doing data analysis a lot of the time. Yeah. I think most of Wikipedia that's related to math is written by mathematicians, and they tend to try to be as exact as possible with their language, but then it's really hard to understand. Yeah.
It's the same as science. They're all written by, I think, postgrads at MIT.
Anything is written in category theory.
Yeah. Even Einstein, like Einstein's summation notation is quite complicated when you get down to it, but the use case for us is very simple.
Actually, I think category theory is probably a bit more precise than that.
Yeah. But so what is a tensor? I just gave you the definition, but I'll give you, so any like array of numbers is a tensor, and even just a single number is a tensor. So you can one way to differentiate tensors is by their rank. So this is like a scalar is a rank 0 tensor, a vector is a rank 1 tensor, a matrix is a rank 2, and like this is a rank 3. We don't have a name for this, except we usually call something rank 3 a tensor, but you could have something rank 4 that's also a tensor.
I think that is a slightly simplification than maybe computer science, but in physics, can also have tensors, but it's actually defined on how it moves stuff about.
Mm.
And I don't know whether you come to covariant tensors and so forth.
Yeah, there's a lot. There's a
Yeah.
lot of that with, but I avoid it because it's not
Yeah.
how we use.
Exactly.
We think
yeah.
of tensors in
quite
machine
more
learning.
complicated than it needs to, but with certain calculation, it's quite useful. Yeah.
Thanks. So I just some things about tensors. Like rank is one word for what we've been discussing, but you can also think of it as like degree. It's also called degree or order. And then each rank can be thought of as like an axis. And each axis has a number of components or dimensionality. So for this vector that's of rank 1, like let's say the first rank has 5 components. For this matrix, maybe the first rank is the rows, so the rows have 4 components, and the columns have 3 components. Just to have some terminology, but it actually changes a lot when you get to this part of when you're looking at it. But anyway, we use tensors all the time in deep learning, and we use them in 2 ways usually. One is to represent our data. And then that's what each axis tends to have some meaning. Like usually you have like your batch axis where you're batching different data points. And if it's a time series, then you have your sequence axis, and then you have your features. And then you also have so this is where we view a tensor as a data, but then we also view it as a linear mapping. And that's when these are like the weight matrix in a model that you might have. So you have like your input axis and your hidden layer axis. So this is the input goes in here and the output goes out this way. Yeah. And so, sorry, just to go back. And so when I say we use tensors in deep learning all the time, how do we use them? So we have these 2 things, like your data that's a tensor, and then your weight matrices and everything that's a tensor. And what we do is we define operations for different tensors operations. So we have like matrix multiplication, dot product, element-wise multiplication, transpose. There's quite a few other ones, but we pretty much know all of them. So to operate on these 2 things, we define these operations. And then we also have to define some broadcasting rules, because like these tensors don't have the same rank, they're not the same shape. So you have to figure out like how do I like do matrix multiplication on this, which is like a really common thing within the linear layers of a deep learning model. So you usually say like, okay, this first column is going to go to this column, this second column is going to go to this column, this third column is going to go to this column. But actually, this was one of the things I found out when I started using the einsum function, is like broadcasting isn't memory efficient, because what the computer does under the hood is it will copy this matrix 3 times in order to multiply each one of these batch points by the matrix. So this is just one of the motivations for why you might want to use einsum.
Although that's specific to PyTorch, not some fundamental.
Yeah, it's more like most implementations do this.
Even
I don't know. Maybe it's because it was easier to implement or something along those lines. Because I think a lot of functionality implemented once, and they're like, okay, if people complain, we'll optimize it. And that's why like matrix multiplication is super optimized, but maybe like broadcasting isn't. Or what I've found is when you look at the source code for a lot of libraries, like PyTorch or JAX, like the deep learning ones, when they're doing broadcasting, they're actually using the einsum function under the hood. Yeah. So why is the einsum function useful? One, it can perform many different operations using a single function. So like all the things I talked to you about before, like dot product and matrix multiplication, element-wise multiplication, transpose, it can do a ton of different things that we do using a single function. It does not create, sorry, I should have mentioned. the reason why broadcasting happens is because you'll have tensors of a different rank, and usually you like copy the tensor of the lower rank multiple times. So it does not create copies of the lower rank tensor using up additional memory, and you don't need to do reshaping of tensors to meet broadcasting rules. This was actually the main reason why I found this attractive, because I've written a lot of different like algorithms with deep learning models, and I've just written a lot of code that has to do with like reshaping it into the right shape for like a different layer or for an algorithm. And this just removes the necessity for this. That's the main reason why I wanted to use it. It's often, but not always, faster than performing the operations using broadcasting or a series of operations. Often, but not always, based on what I read. It's used in algorithms and papers from time to time, like if you look at algorithms. Here's some papers in like recent ICML, SCLR, and NERFs where they used it. I also remember there was one paper that we did in Paper Club where the algorithm was written using like with pseudocode using the einsum function, but I couldn't find it. I spent a while, but I couldn't find it. So it's useful to know because you might see it in a paper. And lastly, it's used in deep learning packages, source code. So like this is JAX's source code for computing the log likelihood of a multivariate normal distribution. And you can see it pops up here, here, in a really simple way that we'll go over later. But so you might see it and be like, what the heck is that? Oh yeah, and the last pro is that it makes code and algorithms involving tensor operations shorter and simpler to write down. The con is that learning Einstein summation notation used in the function in einsum can be tricky. So like that's why I wanted to practice a little bit today with you guys. Introduction to Einstein summation notation. So actually I wanted to start with a disclaimer. The stuff I'm teaching is I'm simplifying Einstein summation notation because in actual Einstein summation notation, superscript and subscript have meaning, but the einsum function can't distinguish between the two of them. So actually, I'm going to be teaching you Einstein summation notation as if there is no such thing as superscript versus subscript. And that actually goes to what you were talking. The reason why they have that is to do with what you're talking about before, like covectors and vectors and contravariants and variants. So what does Einstein summation look like? It's actually quite simple. So it usually is just removing the sum symbol from an equation. So here you have two vectors. This is calculating the dot product of those two vectors. And instead of putting the sum operation and having to specify like the size, which you actually don't always have to do, you can just write it like this. And that's really the main idea. There's a lot of, I think there's actually some abusive notation in Einstein summation notation where you can use it for more than just this. But
was recently one paper we presented where they did that, where they had the same index, but then they had actually superscript, which is also an I in this case, and you didn't know what they actually was coming over was maths.
Yeah. But why was Einstein summation notation created? It was created by Einstein. It's to make writing proofs and equations related to tensors simpler. So instead of having to write, it made proofs a lot shorter, I think. But also because it made them simpler, it makes it easier to prove things in tensor calculus. So I want, yeah.
Which often you, of course, work with real space, like some over X, some over Y, some over Z. In that case, it becomes just whatever you're summing over, just what you use there.
Yeah, exactly. So it becomes a lot shorter. And I think this is interesting because it's like there's probably problems that Einstein could only solve because he changed the notation, which you would think maybe isn't a meaningful change, but I actually think it's quite a meaningful change because of the fact that just by making something a bit simpler, you're able to solve these problems. It's easier to solve.
I think the issue with you is developing general relativity.
Yeah.
I think that was the conflict.
Yeah.
And somewhat very. And in general relativity, we're interested in tangent spaces at a particular point on manifold. And that's where, but then the issue is that you need to put some sort of basis and there are different bases that you can choose.
Mhm.
And when you choose a basis, that's when Einstein notation comes in. The eyes refer to the axes of your chosen basis.
Yeah, yeah,
At that
exactly.
point in space or space time. Or whatever.
Yeah.
Comes quite useful when you have things like magnetic fields. I mean, the magnetic field is a vector product of flows, right? And you can show that certain sums over certain anti-symmetric things become zero. So that's where it becomes very useful.
Mm. And also when you're trying to do a lot of tensor operations in deep learning. But for a completely different reason, like you guys are pointing out it was built for a completely different purpose and is very good for that purpose, but also good for this one. So what are the operations it can express when we're not thinking about the difference between superscript and subscript? Is element-wise multiplication, summation along an axis, and transposing in tensor. You can express all of those things together as a single operation with Einstein summation notation. And what are there's like 3 rules that define Einstein summation notation. That's a joke. That's not actually the first rule. But so Einstein summation notation is all about adding index variables to equations in order to describe the equation. So one rule is that any twice repeated index in a single term is summed over. An index that is repeated twice is called a dummy index. So here, in the equation here, J is a dummy index. And this is actually, this equation would be multiplying a matrix by a vector to get a vector. And you can see that like by multiplying the J by B, you're calculating the vector. The second rule is that an index which occurs only once in an expression is called a free index and cannot be replaced by another free index. I actually didn't really understand what this rule meant, to be honest, because I was thinking like I could replace, so the free index here is I. I'm like, I could replace this variable with any other letter or whatever symbol I want and it would be fine. So I didn't exactly understand.
You'd have to change what to do as well, right?
Yeah, well, no, actually it doesn't matter. It's Einstein summation notation only is within like a term. So each term can have its own set of variables. So I could make this like Z and this F and it wouldn't matter.
It's only the J's within the AB term. Is that right?
I think that you can easily swap the J for K's because it's summed over, right? But,
Yeah.
but the eyes must be the same.
Think so?
Because essentially you're saying you add the ice component of the B vector to the ice component of the AB.
Yeah, true. Okay, that I guess.
If you change that, it could mean it's different things. So if you take it back around and sum over I yet again,
Yeah.
then it's very clear that you change that.
Yeah. Okay.
Some rotation of I. But
I'm glad I got you guys in the room.
Do you have a worked example?
What?
Do you have a worked example? Because I looked over this before and then thought a bit clueless. So
Yeah, we're gonna go over some stuff.
I found a blog post on the einsum thing, and I think actually it's much clearer when you go to einsum because everything's quite clearly defined.
is that the one you sent out?
I think that's good.
Oh, right.
You
Yeah.
said there's a
Oh yeah.
Implementation of it.
was a blog post somewhere. I can't
Yeah.
remember what it was actually. But I always found the Einstein summation a bit hand wavy and not that clearly defined. And I always thought behind it there was some form of calculus, like some little system that you write down, but physicists never bothered to do that. But the nice thing about the einsum notation is that they do, and so it's actually very clear because I'm sure you can answer this.
Well, we'll see.
It might become clearer.
Yeah. But that does make sense that the within a term, if a free variable only occurs once, then that you can't replace it with another one. And no index can occur more than 3 times or more in a given term. So like here, J is used 3 times, and and this is not good, but you can use it twice. So those are the three rules of Einstein's summation notation. But now you're making me wonder if those are just the rules from like the research that I've done that I found. It's like I found someone who's like listing the rules. But if it's not super clearly defined, then maybe these are just like someone's interpretations of the rules.
It might be. I may just not have been paying enough attention in lectures.
Because the last line looks wrong to me. Because we say on the right hand side there's no index allowed, right? Because we sum over something that has a dimensionality. And there must be a scalar, right? And scalar has no index, so otherwise it would be a vector.
Yeah, so this actually is where I feel like there's an abuse of notation.
Yeah.
Because this actually, what this means, at least according to my understanding, is the diagonal of, like,
Yeah.
give me the diagonal of the matrix. CJ is the diagonal of the matrix.
Exactly, the trace, right?
Yeah.
That would be a single.
No, not the trace, the diagonal. By doing JJ equals CJ, if this was just a scalar, if it was just C, then there would be the trace. But this is saying, give me the diagonal. Yeah,
So that's like sort of broadcasting it already, or?
yeah. Yeah,
I think to get the diagonals, it can be extra devices and
Yeah.
other variables that
Oh, yeah, you
something,
need,
yeah.
yeah.
This doesn't feel quite right.
It doesn't to me. Okay, so we've gone through like a very poor introduction to Einstein summation notation, but let's do the Einstein function because I'm hoping that will be simpler.
all the inputs I've ever seen have been.
Yeah, not great.
But as I said, when I was reading the book, it's the Einstein formulation made it a lot clearer.
So, what does einsum look like? So here's some examples of what it looks like. So you have two-dimensional, order 2 tensors, like two matrices, and you're doing matrix multiplication. So you're saying ij times jk equals ij. It's basically saying, okay, let's keep the first axis and the last axis of the two matrices, and we'll multiply element-wise the second axis of the first matrix and the first of the second, and then we'll sum them. So this is matrix multiplication. If A and B are vectors, then this is a dot product. So you're just saying, like, okay, give me element wise multiply I, and then just sum them. This is a matrix transpose where you say, like, okay, just switch the axes.
Yeah, the dot product is weird.
Yeah, I think the dot. I think the dot product should actually be. And this is my mistake. It's just because this.
It is kind of confusing because the comma, a comma here means a different. Like,
Everything's within a string, and you're using the function.
yeah.
Mm.
So the first one it's ij and jk are the first argument of the
Okay. Make this a little bit bigger. So, where is this? Okay. I don't know. Wrong view. Okay, there, and I need to. Yeah, so dot product would look like this because you do want to sum. Matrix transpose like this, so you just switching the letters. One suggestion I have based on having used the einsum function is, like, as you can see in the dot product example, you don't have to say point to something, but then they have like a lot of rules that are used to decide what to do. And if you don't know those rules, you might not be calculating what you want to be calculating. So like another way of doing matrix transpose is just with JI, because it alphabetically reorganizes the letters that you give it as like a rule for the einsum function. but you don't necessarily want to do that. But anyway, these are just some examples. We're actually going to work through some. I just wanted to show you kind of what it looks like. So it's like a string describing the operation and then the tensors that you're going to operate on. So there's a couple of limitations of the einsum function. One is that you can only calculate a single term in an equation expressed by Einstein summation notation. So you can calculate this and this, but you can't calculate them together. There's no way of doing that. So yeah, you can only calculate a single term.
Then you have to do both.
You would probably just do like einsum this plus einsum this. Yeah. And then the other one is that einsum cannot distinguish between vectors and covectors, and that has to do with the fact that it can't distinguish between like superscript and subscript. But this isn't important unless you're trying to, like you're doing physics where, as we've kind of talked about, there's a very different interpretation or use of tensors than how we use them.
So it's like the einsum function in a way, just like that, or it's like pasteurization.
Yeah,
It's sort of like this like looks convenient
you could.
for us to express like tensor operation, but it's not actually
I actually think.
summation notation.
I think you could. Yeah, it's not exactly. The reason is because like the one operation that you can't really express that's required is kind of like you can transpose a matrix within this the notation used for einsum, but you can't take its inverse, and you need to take its inverse in order to like distinguish between vectors and covectors. Because my understanding is like a vector is transformed into a basis, and a covector is transformed into the basis, which is the inverse of that, the basis that you can transform a vector into. And so einsum doesn't allow you to do the inversion of a matrix. But that makes sense to me from the point of view.
I think it always goes back to some base matrix where it is defined that a base matrix EI in the covariant space is EI in the regular space, the way exactly delta. I think it's quite useful because you can, in the previous example, also do like in unorthodox matrix multiplication, like swapping this indices for square matrix. You don't have to kind of hold that.
Yeah, exactly.
I'm trying to think what the practical implication is of not having up and down. Would it make this a little more linear? Like, is the actual Einstein summation in physics more constrained?
It means that the vector here, when you do whatever you calculate, might not be a true vector anymore. Vector is something that when you rotate it in a certain way, rotates as well. This is not necessary for stuff like magnetic fields. When you rotate or move the fluxes that generate them, then actually magnetic field might not rotate like that, but it's still going in the other direction. That's where things get weird. Because you don't care about weirdness.
Yeah, exactly. Everything's like a lot of the linear algebra that we use is very simple. So let's do some examples of the Einstein summation notation in the hopes that, and then at the end we'll do two actual working examples for you. But so my question is like, we don't have to do the NumPy equivalent, but if A is a vector, what do you think this call to the Einstein, like to einsum, would give you?
Yeah, it's component, but it seems wrong.
Either the ith component or it's just
Did the vector do the sum of the components?
So Jerry, you're right. It would just give you back A, because it's just saying like, okay, take every single value. Not that it's super obvious, by the way, as we'll see. Like, I'm just like I want to show you guys examples so you know what happens. But yeah, this would just return you A.
I've forgotten what is that? Is that shorthand for the arrow? Like, can you write that with an arrow? Like, is that just shorthand?
If you
An
did,
expression with an arrow?
yeah, that's shorthand. If what you could do,
Is that just shorthand for I goes to
I
I?
to I.
yeah, this would just be
Identity.
And that's one of the reasons why I prefer, my suggestion is like always add the arrow.
Yeah, that was my conclusion. Always have the arrow.
And then,
You just invite in couple.
what do you think this is? Like the
That's
second example.
That's then what having this, probably this one, this one.
So actually, this one is, but it's not obvious. But it's more to understand. This one is summation. So this is sum up the vector.
You don't really have a repeated index, right? So it's-
Yeah. It's just like sum the vector. What do you guys think this one is? So A and B are both vectors here.
Scalar product maybe, but why is it still an item? But because scalar product is a number, not a vector.
Well, you can do that,
Is that just pointwise?
yeah,
Yeah, I think it's pointwise multiplication.
so you end up with a vector of the same dimensions.
Yeah.
I'll have to find the book.
Right. Yeah. But that's very implicit. Yeah.
What do you think I is?
That must be the scalar product.
Yeah, I think this one is when you say scalar product, I think this is a dot product, but I don't remember exactly.
Yeah.
Yeah, dot product.
Isn't it the same, no, same thing? It
ends up
as a scale.
Yeah,
Yeah.
scalar product.
You write that.
Yeah, you're right. Scalar product.
You write that fully with the arrow.
Yeah, so without the arrow, you can say like, I guess that means like sum to a scalar. So by the fact that it doesn't have going to I, maybe this arrow is just always assumed to be in there if it's not there.
So there's no arrow, just assume it's arrow.
Yeah.
Except the first one.
Except for
Yeah. And well, when we go to matrices, there's other examples. And then what do you think this is? This last one, two vectors like that.
Cross product.
Yeah, cross product. So it's saying like, okay, take the ith element of J of I of A and the jth element of B, and then you're just going to put them together to make a matrix. Okay. And
what do you mean the outer product?
yeah, cross product.
Yeah, right. Cross product is yes.
Yeah.
And tensor, epsilon tensor. Yeah.
Outer product. Yeah. So let's do some stuff with matrices. Okay. So what do you think this is? Yeah, identity. This, yeah, transfer. This one,
Well, again, I think it would help to put the arrow in, of course, because there you're relying on conventional alphabetical order. Whereas
Yeah.
If you put the arrow in, then you can explicitly you can put it in the variables like it.
yeah, exactly. I agree. This one,
I think you would just have the trace and it's pretty second. Edge is diagonal, right?
Yeah.
Yeah.
so this is these two are like where I feel like there's an inclusive notation. Because it doesn't make sense to me that you could use it to like remove elements to extract specific elements from a matrix. Like that.
So the third one returns diagonal.
Because you're using it twice here. So this one returns the diagonal. Because the reason why I say that is because by the way they're using it, the fact that it appears twice, there should be a summation.
Yeah.
But there's no summation if you do it like this. It's just like you're extracting the diagonal.
As you saying, you think. So, yeah, we sort of force it to be a vector. That is the only way that somehow makes sense. But there's probably a more explicit way to speak that.
Yeah. What do you guys think this one is? The fifth one.
No, this is probably intentional. The conventional scale.
Yeah, sum up the elements of the matrix A. So they're saying take every ij, the I element j element, and sum it all to give us the matrix. Here's what this one is.
So IJ is different from IJ arrow.
Yeah,
I guess that one's like sum across the rows.
Yeah.
Or some person.
One or the other. To be honest, the way that I implement it is that I check to like I'll check on it. I'll like make a matrix or a tensor, and then I'll check to make sure it's doing the correct one.
Yeah.
Because it like or I can look at this table.
It's also easy because the process is simple.
Well, it's simple once you know it,
Yeah.
but learning it is it's it's like
If you make sure that the dimension is different.
yeah, exactly.
Yeah.
So yeah, this one is sum down the columns of A, and this one is sum down the rows. This is actually this is a good point. This was something that I found confusing when I was implementing it because I thought that matrix multiplication would be you'll see what it is, but so you'd expect if it's saying like sum I, which is what it's saying here, right? Because there's no I here. You always think like row column. But it's actually the opposite. So if the first one represents columns and the second one represents rows. So if you had right here, you're saying IJ goes to J.
Yeah.
And usually when I think of a matrix, I'm thinking like the first axis is the rows and the second axis is the columns. But for Einstein summation, for einsum, it's the opposite.
It's physics.
What?
It's physics based. Like, again,
So they do it the other way around. Okay.
I was interpreting that more as like, I don't know, maybe this is too literal with like how do you store it in tensor, but I was thinking like you have the I in the J dimension, so you keep the J dimension, which I interpreted to be like how many columns there are. And then you use sum, you like squish it, so you have the same number of columns. You're gonna sum you sum like all the rows together.
So it's a bit confusing because in the NumPy one, axis 0 means you know you're going to end up with a row, and I'm not getting that intuitive feeling from the einsum.
Yeah, it's definitely something you have to work with to get used to.
That's why I was like, this the I disappears. You might be completely wrong. It's how my brain is interpreting it. Like the I disappears, which is so because you're doing axis equals 0 because we're switching the rows. You get rid of the 0th dimension in a way. You're summing across it. Yeah.
Okay, so we've done that. Now let's do some matrix stuff. Okay, so now we have two, let A and B be matrices. So tensors of order 2. What do you guys think this one is?
And then twice multiplication.
Yep.
Oh,
Nice. First time.
heck this.
What do you think this one is?
Yeah, but why is it IJ at the end?
No, it should be a scalar, but it's exactly the edge at the end.
There's some kind of multiplication.
It's like the scalar, but broadcast to the whole matrix.
So it's element-wise multiplication, but where you transpose the second matrix.
Okay.
What if that? Well, what if the dimensions don't work out?
Then it would
Oh,
they have to be able to work.
I see.
We can just figure out how to figure it out.
Yeah. It's won't work.
Next one to make it more.
I think it's
I think. Oh no, where's the arrow? Oh,
Yeah, it
okay.
is matrix but because it doesn't have the arrow, I'm like, it should,
Yeah.
I think it is matrix multiplication because we'll see. But that's what, again, always use the arrow. It's so much clearer when you have the arrow there.
If you don't use the arrow, is that more in the spirit of Einstein summation? Because then you're left with just conventions about the people you see.
Yeah. I think it's Einstein plus or something.
Yeah.
It's also quite funny that Einstein means lonely.
No, really.
Yeah. It's like
Einsam.
Einsam. It's slightly different spelling, but it's different. They always think like guy makes probably
Oh,
in German, I mean,
Einsam.
in German.
Yeah.
Brahms is frei aber einsam, free but lonely.
Yeah.
Oh,
Yeah, FAE is one of his.
Okay, so this one we think is matrix multiplication. We'll find out at the end. What do you guys think this one is?
I would say I'm also looks matrix. Multiplication. I think you call it like a dense operation where you sum over.
What? Yeah. So I think it's A times B transpose, but where times is matrix multiplication as opposed to element-wise multiplication. This one, these ones, yeah, this one's tough. This one's a tough one. Good luck.
It's like for each index we have a vector j that you can essentially multiply b times that vector and sum it up, and then put that into a vector which then becomes a three-dimensional tensor, something like this.
Yeah, so it's this one. I think I'd have to actually do a couple of examples on the computer to figure out, but I know what the answer is. So it's A, I think, multiplied by every row of B, or something along those lines. We'll check afterwards, but it's basically you're multiplying the matrix A by every row of the other matrix, or it's the other way around. You're multiplying B by the rows of B by every one of these. By that, which actually I think could be like a super. The fact that you can express this with Einstein summation notation, I find super interesting, because I've seen a lot of algorithms where they do something like that, and I can't think of a simple way to do that unless you start creating like massive tensors in order to broadcast a matrix for every row. Okay, and last one, and then the examples that we're going to work through are a little bit easier, hopefully. But what do you guys think this one is?
The outer product of matrix.
I know what this one is. So it's multiplying every element of A by B to create like a giant matrix.
This will be the outer product.
Okay.
Is it kind of like you take sort of like add a dimension, add like another dimension?
I think
Do you like copy, sort of like copy the
I think
matrix?
you take the matrix, each matrix, put it into a vector, take the outer product, and then reshuffle it again that it gets the number of registers in the same order.
So I think you could also interpret it as like for every element in A and every element in B, there should be an element in this new tensor that's created,
Yeah,
because there's 4 indices here.
right. I see. Algorithm.
This is how it's supposed to be done.
Yes, so you kind of like expanded the.
Yeah, each row of A multiplied by B. Let's see if we can tell that. We can see that.
Oh, sorry, the loops. So it's slightly different.
Okay. So we've done some examples, which I think are pretty confusing, but I hope you learned a little bit of something. Now I wanted to ask you guys, what do you think this means? Because we saw this before in the source code for calculating the negative, the log likelihood of a multivariate normal.
Some over the last, you get something that's smaller, but everything else.
Yeah, exactly. So you can use this. If you guys ever use this function, and you just want to operate over the last, and even if your tensors are different, have different orders.
So the number of dots doesn't matter. It's just 3 dots for.
Yeah, 3 dots. 3 dots means like everything except for the last one. I think you can actually do like ij, and you can do like I here or something as well. Okay. So let's see what we've learned. So we have like, let A, B, and C be tensors of order 3 of the same shape. So they're everything the same. assume that you can calculate this. Or say the first axis represents a batch of data. And so if you say the first axis is a batch of data, that means that it's like each point is a matrix. And then you have like multiple matrices that are added to create a tensor. And so we want to, how do you calculate per point in the batch using the einsum function this? So this is matrix multiplication. You want to do A times B times the transpose of C.
But the A and B are three-dimensional.
The NC are three-dimensional. They're all three-dimensional, but like the first axis is your batch of data. Like you randomly loaded some data, and you want to do like a batch matrix multiplication, essentially, of this form. So I can start us out by saying like the beginning of it is going to have to be like I, J, K, because we have our.
It would be IKJ.
Well, it would.
No.
It'd be I for sure, because we want the batches. The batch is the same amongst them. Like the index, we want to use the same index for all the.
But how we prevent the summation happening? And it will be
So maybe first is say we only had A times B. Oh, how do you for this? How do you for I?
Yeah.
We've seen that before.
but by putting I at the end.
Yeah. If it's not there, it's summation. If it's there, then it's element-wise multiplication.
It's not IKJ because we're still a regular matrix product apart from I, right?
So, well, so you're saying it's IKJ, but then you would be.
Going to I. Where the thought.
Going to I.
But
Going to I.
if you did this, then you're going to be multiplying both K and J.
Sorry, JK.
Well, if you.
No, you're right. K L.
Yeah, K L. And I.
We can't even figure out an AB. Can we do an AB first?
Yeah, so let's do AB first.
I thought that was A.
As in what's the right side of the arrow?
Okay, so
AB,
yeah, let's do
or
that.
would be like I. Would be like
J L.
L.
Yep. Hopefully, you guys a little bit afraid of moving. Okay. So this is just A, B.
Yeah.
So if we wanted to include C in,
Just go again. Yes, sorry.
yeah.
The L, when's the L come from?
So the L is so that you say this was J, right? Then you would be multiplying both of these axes. You'd have two summations that would be occurring essentially.
Be the trace of the matrix.
Actually, what would be happening here is you would just be set. You'd do.
Is I the batch?
This.
Oh, perhaps can I call it B?
Yeah,
I think called I B. If you change I to B, it might be.
Yeah. Okay. Here, let's do that.
Because I think.
not capital B, small b.
Yeah, it's more sort of.
B.
I'm not sure the capital B.
So because these are both here, this would imply element-wise multiple, and then this is here. This would imply element-wise multiplication. So this would actually be A, B transpose. So it wouldn't be matrix multiplication if we did it this way. But if we let this be L, then you can't do element-wise multiplication because you're saying this axis isn't the same as this one. And then it becomes A times B. And this has to be. So if they were both the same, it would become element wise. Yeah. Okay. Let's do this one. So we have the first part of it, B, J, K, B, K, L, and then we know this has to be B. What would it be?
And I was gonna say like ML.
I would have, I would have thought IL prime, IL. Yeah, right, ML, yeah.
Yep, that's correct. You guys did it. And then it just becomes B, J, M. So that by having B at the beginning, that means element-wise multiplication instead of summation, even though it's repeated. And then you're saying like, okay, sum these two axes because they don't appear here. And then sum these two axes because they don't appear here. Okay.
Under the hood, is that faster because it would see it as one operation rather than two operations that are compatible, right?
I mean, you fuses them.
Oh.
It's about fusion.
Yeah, I mean, this guy, if we put this into under the hood, but is that faster than if we were to do the matrix multiplication one by one?
Yeah, I think so. But when I did my research online, it was really like a sometimes. Yeah, it's not really clear to me.
I can imagine maybe like if you can write these kind of operations and maybe under the hood, like you're not creating rather than doing it in various steps where you're creating maybe like copies of data or like, I don't know, if it's having to move data around to do these operations. I don't know, maybe there's some collaborative tricks.
Because it definitely knows already what the final array size is, right?
Right,
So it's
exactly.
probably able to.
Yeah, I wonder what the implement, because I suppose it does all those operations. So in C, like in NumPy or something, maybe.
What happens if you add more matrices?
I think if you're, no matter what, it's the same number of calculations, no matter how you express it. So it has to do more with like whether there's extra steps that are involved when you're not using the einsum function. Because when you're using the einsum function, it strips it down to exactly to just doing the calculations that are specified. Okay. This is the last one, and then we're done. And I couldn't even write it down I have no idea how to write it down mathematically. So maybe you guys can tell me what's the correct way to do it. But I described it. So, I'm going to erase this. This is, again, this is something I've had to do before. I think when you're dealing with time series, you'll do it at some point or another. So you have, let A be a tensor of order 3. So it would be like batch times sequence times features. And then, and that's what's described up here. And then you have B, which is a transition matrix. And what a transition matrix does is it would be of size features times features. It's telling you, it's an estimation of what the next time step is going to be. So if you multiply the feature vector for one time step, you're going to, by the transition matrix, you should get what you estimate it to be in the next time step. So if you wanted to calculate the estimated next state based on the transition matrix, which basically means I want to multiply every vector of the batch times sequence number of vectors by this transition matrix, how would you write that in the einsum function?
But the sequence, when you say next state, would that be next state in each sequence?
In each step in each sequence. So you have
I-
so you for your first you have your first element in your sequence. You want to calculate what the estimated next state would be based on that.
And then this is not what you already have as the next state.
Well, it's your estimate of the next state. It might not be the
I see,
next.
I see, I see.
Yeah.
So the output, what's the shape we want of the output? So like, it's
Especially-
batch by features.
Batch by sequence by features.
So like sequence plus one.
Or no, because you're for each one you're estimating the next
Okay.
state, so you don't have to keep the first one.
Ah, okay.
Yeah.
All right. So you kind of just want to like.
So yeah, you would want to, you have a feature vector. So you might say this is of size 1, and this is of size 2, and this is of size 3. So it means you have actually you have two feature vectors only.
Yeah.
And you want to and each one is of size 3. You want to calculate for each of those two the next state estimate. So I'll start us off. Start is going to be, we'll do batch, we'll do sequence, and we'll do features.
The alphabet is hard.
What? Yeah.
Now we have the arrows.
Depends a bit on how the transition matrix is defined, whether it's.
Let's say it's by right multiplication.
It's always been what FG.
Or GF, then it's like.
Oh yeah, you're right. If it's right multiplication, it's right. Yeah. Because of the how it switches. Let's say it's left multiplication.
Yeah.
So if this is the operation, what should I write here?
ESG.
Yep. Okay. So yeah, like usually you'd have to write a for loop or make this into the same. It would have to become like batch times sequence times features, make it much larger in order to do this operation. But with einsum, you can just write it like that.
But like in like PyTorch or something, can't you just do like can't you just multiply and do
I think
like if
it depends on the broadcasting rules, and they're different between NumPy and PyTorch.
If the sequence, if the sequence is a specific size, then it maybe just fits one of the other rules because precedences, might be right. I don't know, but I could imagine something like that happening.
I think that with NumPy, it's like left broadcasting, and with PyTorch, it's right.
broadcasting.
So if you made this like 1 cross 1, maybe it would work, but you just still have to expand the shape. But instead, you can just use einsum, and you don't have to worry about broadcasting
No
rules.
more reshaping -1, 1.
Yeah, exactly.
Which is cool. I
Yeah.
think I'm definitely gonna try that.
Yeah. I just have had to do it. So yeah, I'm not going back. That's my. But I have it. I think I did it wrong. Where I'm assuming B is A. So we're just gonna move past this slide because it's wrong. But anyway, thank you for listening. Questions? Yeah, I don't know if we'll ever see people adopt the einsum function. It's very niche, but
I mean, I think you do see it in the libraries. As you pointed
yeah,
out.
because
And I was quite happy to sort of read about the einsum function because that always looked rather mysterious to me when I just happened to see it in the libraries and all of these arrows and stuff. And so it's nice to know what that means. And it is, it's a lot simpler. Oh yeah, and it's also and it's like really
Thanks, everyone online.
really concise to write down the definition of wave potential.
Yeah, true, that too.
Did the blog post have that?
It did. And I will find the blog post and I'll post it to the meetup.
Yeah.
Okay, that would be great. Was it quite complicated?
No, it's very
Thanks,
exciting.
everyone. I'm gonna stop recording and everything, but thank you for coming.
Matrices, like, it's like, you can write that, like, we can use.
Yeah.
Yeah.
And then of course you can have the bachelor's.
Because at the end of the day,
Yeah.
we have